So in this problem, they start by giving you just two reduction half cell potentials, and then ask, what is the cell potential, which would involve just the overall cell potential if you hook these two half cells up. But it could also just be like pretend that you mix these two things together where you get direct electron transfer between these atoms. All right, and so again, it's going to be the standard procedure. You look at these, you realize that the thing that is more positive is the one that would occur as written as the reduction. You find the more negative thing, you turn it around, and when you turn this around and write it as the oxidation, that changes the sign to a positive 0.74 volts. And the overall cell potential is going to be the potential of the oxidation half cell plus the cell potential of the reduction half cell. You add those together and you get the overall cell potential. All right. One thing to note about this is that the sign matters. All right. If you are doing the overall voltage for a reaction that actually would occur, a reaction that is spontaneous, all right. And if you're doing any type of voltaic cell where it works, all right, the reaction that's happening is going to be the spontaneous reaction. You should end up with a positive number. All right. In the next problem, we are given, one second. Okay, it asks for you to formulate a half equation for the reduction of bromate ions, and this is bromate. And by the way, I didn't put all the parts to this question in the what I provided you, but this formula right here was provided in an earlier question. All right. One thing I've noticed is that it doesn't appear that the data booklet has formulas for all the polyatomic ions, and it seems like for most of the polyatomic ions, except for things that are very common like sulfate, nitrate, for example, that they would provide that for you. All right, so this is bromate, and it can get converted into bromide. So what's the half reaction? All right, so it's going to be the same. It's going to be the same process, all right? First of all, let's show this going to this, all right? And remember, you go through this process where you add water molecules to one side to compensate for missing oxygens, then you add H pluses to the other side to compensate for to balance out the hydrogens, all right? So if we look at this, there's 3 oxygens over here, there's none over here, all right? You want to look at your non-oxygen and hydrogen atoms. All right, so that would be bromine here, and make sure that those are the same. All right, so we've got 1 bromine over here, we got 1 bromine over here, so we don't have to multiply one side of them, put a coefficient of 2, for example. So since that's 1 bromine on each side, we just now move on to looking at the number of oxygens. So we've got 3 oxygens over here, so that means that we have to add 3 water molecules to this side. And because we've got the 3 water molecules over here, we've got the 6 hydrogens, so we need to add 6 H pluses over here. All right, so now we're at the step where we want to add electrons to balance out the charge. And overall, this has got a +5 charge on this side. This has got a -1 charge on this side. So what that means is we have to have 6 electrons on this side. We need to add 6 negative charges over here, so that the overall charge over here would be equal to the overall charge here. We do that by adding the 6 electrons here. So that would be the overall balanced equation. And again, make sure that you're giving the states of matter. All right, whether if it's dissolved in solution, you say aqueous. If it's a pure liquid, you would just say L. If it's a gas, you'd say G. Okay, in this problem they say bromate ions oxidize iron 3 ions to iron +2. Actually, that's the same thing. They're saying that's the same thing as iron 2 ions to iron 3 ions. All right. One thing, by the way, in my opinion, it's a little bit redundant to put this Roman numeral 5 after bromate, because by definition, bromate is this ion right here. All right. And if this is what bromate is, the oxidation state of bromine within that polyatomic ion would always be 5. All right. Notice that here, when you're talking about iron ions, sometimes iron can be in its +2 form, sometimes it can be in its +3 form. So the Roman numerals here actually make sense, but here I would argue that that's a little redundant. All right. Anyways, it says that the bromate ions are going to oxidize this to Fe3. All right. So we have, and you'll notice one thing about this. These are all part of question 7, which means that it probably refers to something that's been stated before in the problem. All right. And so we have this the half reaction right here that shows bromate being reduced. All right, so that means that bromate is an oxidizing agent. So what that means is that this is actually going to be the half reaction that bromate is going to be involved in. All right, so I'm going to go ahead and write down that half reaction that we determined in that previous step. And we're going to show, we know that iron is going from its Fe+2 to Fe+3. All right, so pretend that the 6's were not there. All right, we just had Fe+2 going to Fe+3 plus an electron. All right, well, why do we add the 6's then? All right, because we know that, all right, for this to balance out, we have to have the same number of electrons that are provided when this thing gets oxidized as are consumed when this thing right here gets reduced. All right, so since you get those 6 electrons here, we need these 6 electrons here. And to do that, we have to basically scale that iron. We have to scale that iron reaction up, which you can see here that this is the actual process that's occurring there. All right. And then all we have to do is take the 2 reactions and we add them together. Notice that your electrons cancel out, and you'd end up getting this. And again, and it's a little, you have to be really careful. And again, here I should have aqueous in parentheses here, and I should have parentheses with an L after that. All right. I know that when you're doing this, a lot of times anytime you have an ion and it's in water, you know that it's going to be dissolved, all right? And so you have to kind of force yourself to write that, because anybody looking at this that knows, is relatively knowledgeable, would understand that this is dissolved. And they understand that water is going to be in its liquid form. But they do require that you put those in your answer. Okay. And the next problem, it says calculate the standard Gibbs free energy change in joules of the redox reaction. In one, I'm not quite sure what that refers to. It probably is because this question comes from past IB exams, and the way it was written in that particular paper copy, it referred to something that had this Roman numeral. All right, I'm pulling these from a computer question bank, so these things, all these numbers are not the same as what you would see in the original paper copy. All right, but they mentioned using sections 1 and 2 of this data booklet to figure this out. All right, so they provide this information right here. And why do they provide this right here? Okay, that's because in your data booklet, the only thing that you have potentials for as far as half reactions are in this chart right here. And notice that particular bromate to bromide half reaction is not something that you see here. All right, we see this permanganate going to manganese ion, but there's not a whole lot other than like one atom going to the same atom with the same charge. So that's why they had to provide that part in this problem. Okay, another bit of data that we need is the electromotive force, or the cell potential for the iron reaction. And again, it's provided in that data table as a standard reduction. All right, but what we're doing in this reaction is actually having the iron getting oxidized. All right, so we need to turn this around so that it shows Fe+2 going to Fe+3. And when you do that, you just change this from a positive potential to a negative potential. All right, but when you combine that with this half cell right here, and I know that the cell potential because they provide it right here. Well, when you add these two things, notice that you still get something that's a positive value, which would mean it would be a spontaneous process. All right. So the next little bit that we need, they mentioned that they use section 1. All right. Okay. So the reason that section 1 is needed for this problem is that there is this equation right here that relates Gibbs free energy change with the electromotive force that's created by this electrochemical reaction. All right, so this is going to be your cell potential right here. F stands for Faraday's constant, which you can find that right here. All right, and for right now, I don't want to get into the units here. I'm just going to say we're going to use this number when we have F, and N refers to the number of moles of the electrons that are transferred. All right. So again, the N is the number of electrons that are transferred. So if you take a look at the overall balanced equation, notice that there were 6 electrons that were transferred. All right. So that's what that N refers to. All right. So we also have this relationship. We know that the overall electromotive force of the reaction is the oxidation plus the reduction. So we calculated that right here. All right, so that's going to be the overall electromotive force of the entire reaction. So that would go right here. All right, we plug this in for F. All right, here is our E, and here is the 6, which corresponds to the number of electrons that were transferred there. That gives you this calculation right here. So one note about this, at least in the year that I'm creating this video, I haven't gone over this reaction in class, so I do want to expose it to you, but at least on this quiz coming up, you will not have a problem that involves this particular reaction. All right, sorry, this particular equation. All right, in this problem it says in acidic solution bromate ions oxidize iodide ions. All right, so they give these 2 equations right here, although I think that you could have done this even if they hadn't put this here, because you want to, it says oxidizing iodide ions. All right, and if you had access to the data booklet and you just looked at the half cell potential chart, you could find this reaction. All right, regardless, if we're going to show this as iodide ions being oxidized, all right, we're going to, basically we need to, and it's going to be the opposite of what you would see in the data booklet, all right, because those are all written as reductions. But, well, here is the, this is a reduction half reaction for bromate, all right, I can write that this way. And if I've got this, remember, if it's going to be in the same reaction, you have to make sure that the same number of electrons are being transferred. All right, so you'd need to have 6 electrons. This has only got 2 electrons, so we got to scale this up by 3. All right, so that I just write it like this, and that way, when we combine these 2 things, our electrons are going to cancel out. All right, so I combine all those things. Again, make sure that you put the states in your overall reaction. And one thing I want to point out about this, when I look at the answer that they provide, they put iodine as being in its solid form here. And that drew a little, to me, I can understand why they might do that. Iodine, elemental iodine is not that soluble in water, so they might say it would be in its solid state. But it does have some amount of solubility, and so if you would put aqueous here, I think that would make sense. All right, I don't quite understand why they chose to put solid here instead of aqueous. All right, but because there is a question about this, this is what I would recommend. Whenever you have one of your halogens that gets created, well, elemental halogens getting created in water at room temperature, if it's fluorine, say it's a gas. If it's chlorine, Cl2, say it's a gas. Bromine, either aqueous or I think you could put liquid. I would recommend doing aqueous because it does have some solubility. In iodine, you can go and put solid, all right, because it's not that soluble.